Okay, so just to remind you what we did up to last time, we concluded by some arguments trying to match Newtonian gravity with special relativity that there should be some second rank tensor which is somehow the field which carries the force of gravity, that anything less than that, for example a scalar potential as Newton had, is not adequate. Now we can't go much further with that unless we make some a priori assumption about the nature of the laws of gravity, which Einstein made in 1915 under the name theory of general relativity. So I'm always confused. Did he say theory of general? I think he said general theory of relativity, not theory of general relativity. But he said theory of special relativity. So there's a slight inversion of words. This is the most, I think general theory of relativity is the right name because it gives you laws of physics that are the same in all frames, whether inertial or not. So it's the most general relativity possible. But we won't be getting there today or tomorrow, because to understand how this theory works, we have to learn something called Riemannian geometry, which is a very beautiful subject all on its own. And we are going to make a start today with some very simple observations. Actually, the observations I'll make today are things that you could have done in your spare time with absolutely no prior mathematical knowledge, not even what you learnt in ISER. So let's start with that. Let's consider Euclidean 3-space. It's something that we assume we know quite well. All of physics is based on Euclidean 3-space. Sometimes we use a lower dimensional space like 2-space for systems that live in a plane like interfaces or surface phenomena, or we might use a line if we want to study physics of a wire. So it could be 3, 2 or 1. Abstractly it can be any dimension, but we'll always pick 3 unless otherwise stated. And in this we have a distance law which is very familiar. Is just that 2 points set in this space separated, so one of those points is labeled by the coordinates x, y, z, and the other point is x plus dx, y plus dy, and z plus dz. And then we want to know what is the straight line distance between those 2 points. And this is a very straightforward and obvious formula, which is just that the distance is the square root of the sum of squares. We know this very well. It embodies essentially Pythagoras theorem repeatedly. Okay, so these coordinates are called Cartesian coordinates. And I'm pretty sure that in school you learned that there's a frame which follows right hand rule, x and y and then z, and that we can transport it, and if we rotate the system then we can as well think of rotating that frame and measuring vectors and things in that new frame and so on. Very good. They are particularly simple, but there's another set of coordinates which are not so well loved but which are very useful, which are called spherical polar coordinates, in which the distance is given by this. Now it's actually hard to do physics without these coordinates, and I'm sure you have used them repeatedly. They are particularly useful because they simplify the results in spherically symmetric systems, which are very common things. Like if I have a point charge, then the whole behavior of physics around it is spherically symmetric, so these are good coordinates to use. There are others, not so popular, but also used, like parabolic coordinates or elliptic. There are various kinds of coordinates you can use. It all depends on the physics problem you want to address. Now, I suppose you know how to go from this set to this set. The way you do it is to write x, y, and z in terms of r, theta, and phi. And the formula is this. The standard, you can make it go however you like, but x is r sine theta cos phi, y is r sine theta sine phi, z is r cos theta. And with this transformation between these coordinates, from these coordinates, if you insert this into this expression, you simply get this expression. There's nothing much to do. It's simply chain rule. When you have these formulae, you write dx is dr times all this plus r times cos theta d theta times this, etc. You just take d of everything in sight, and then you just throw that expression back in this, expand, cancel a lot of terms, and you end up with this. And this has some interesting difference from that. Here, the distance, amount of distance by moving a coordinate distance dx or dy or dz, the amount of that distance that you move is the same no matter where you start. Namely, it doesn't depend on the xyz where you start and you're measuring this distance. Okay, if x, y, and z were 100, if x was 100 and dx was 0.01, you would get some distance. If x is 0 and dx is still 0.01, you get the same distance. It doesn't depend on x. It depends only on the amount of dx. Now, spherical polar coordinates are not like that for a reason which we actually know extremely well. Just imagine I have 2 points. Now I'm just drawing in a plane. I'm using plane polar coordinates. So I'll call that angle phi, which goes from 0 to 2 pi. And the amount of d phi, so if this is a point and this is a point, they are related only by a shift d phi. But the amount of distance you travel to get from one to the other definitely depends on where you are. So this is the amount, this angle is the amount d phi, small angle. But the actual amount you travel when phi shifts to phi plus d phi is this if you start here, but it's that if you start there. And that explains this factor r in front of d phi. The larger r is, the more you shift when phi shifts. So it's a position dependent distance element. Such distance elements are called metrics. And we are trying to develop for ourselves by little bit of guesswork what are the properties of these metrics and what is unusual about different ones. So Cartesian has a very special feature which is actually extremely rare in general, that you can just write it as a sum of simple squares. This is also a sum of squares, but it is such a sum that in each square there could be a function in front of it. So it's the sum of squares with functions in front. More complicated for that reason. The nice thing is that if I'm in a spherically symmetric situation, let's say I'm localized on a sphere at radius r, then dr is 0. I'm not going to move in the radial direction, and r is fixed. So this simplifies the metric to a lower metric, which is a lower dimensional metric, which is on the surface of a sphere. You've all done this without the words that I'm telling you now. It's all things that you have already used. Okay. Now, you're all very obedient people, so when you were asked to change from these to these coordinates, you never said, can I change to some random coordinates that I just dreamed about last night? Okay, but if you did, you might have come out with this idea. Why can't I use not spherical, polar, not Cartesian, but there's some coordinates which I'm in the mood to use. And for that, for example, you might have said, let me consider start with the coordinate system. It doesn't matter whether I put prime on one or the other. Let's start with this, and let's assume the element is the usual Cartesian one. Okay, now supposing I feel in a mood to write down a formula. X prime is x plus 3y, y prime is x times y, and z prime is z plus z squared. Okay. Just I felt like it. What will happen? And I take this and I calculate d of everything in terms of d of these things, and I put it in there. I'll get some answer. I can't not get an answer. What is the answer? Well, the answer is, when I calculated it, could be wrong. You can verify. That's the answer. Okay, and you can think of anything and you will get some answer. And my question is, supposing somebody said, I have a space whose distance element is this, would you consider it a reasonable thing to study? You would say, well, it's very, very complicated. It has nothing to do with physics. That's not true. It's the same as that. It's the same distance between the same points, just described in different coordinates. It's exactly, it describes the same space, just like spherical polar coordinates describe the same space. This weird coordinate system also describes the same space, though there are some catches which I'll come to in a moment. Now, what can we say about this? First of all, every term dx squared, dy squared, dz squared has some function in front of it, not constants. But I have a new feature, there are also cross terms. That means if I purely move in dx, only this term will contribute, but if I move along x and y, I'll get contributions from this term and this term as well as this term, not just the contributions from x and y. So these don't satisfy Pythagoras theorem in that way, and that's natural because these are not what we call orthonormal coordinates. But now you have to slowly get used to the idea that orthonormal coordinates are a luxury of three-dimensional Euclidean space, of any dimensional Euclidean space. And if we want to study more general spaces, then we might not be able to, though they might not be available, and then we might have to use other coordinates. Okay? But I've not done any geometry. I've just managed to write three-dimensional space in more and more complicated ways. Okay. Now, so let's draw one conclusion from this. So the name for Euclidean three-dimensional space is R3. And you can easily see that my considerations extend to all Rn. They just, for any n, it just becomes more complicated technically, but nothing I've said is really changes. So R3 can be described in any, and I'm putting a question mark here, set of coordinates. And it's still R3. Nothing has really changed. My measure of distance between pairs of points has not changed. Physics has not changed. Okay? The look of the equations will change because my distance element is different, but physics has not changed. So we learn that many different sets of coordinates can describe the same space. That's one conclusion. And it will be true in general that many different sets of coordinates can describe, in fact, the same space. Okay? Now there's one problem with both the spherical polar coordinates and these which I'll call random coordinates because I just thought of them randomly to illustrate a point. So, what is the problem? Spherical polar do have a problem for this reason. It's a well-known problem. What happens if R is 0? Theta and phi don't do anything anymore. Okay. Now, looking at this, you can say, well, this is a three-dimensional space because it has coordinates r, theta, and phi. But around r equals 0, there is no coordinate theta or phi. So I lost something. So r equals 0 doesn't seem like a good point. It's not adequately described by this metric. Okay, at least it's not, there are not three independent directions that I can move according to this metric in R. It looks like there are because I can go radially in all the directions, but exactly around that point I don't see a three-dimensional metric, and in fact the problem is worse than that. Consider theta equals 0 and pi. Okay, so here is my space x, y, z. When theta is 0 or pi, this term disappears. Okay, and that's already a problem. And what does that describe when theta is 0 or pi? Well, actually it describes an entire line, the z-axis. Why is that? If theta is 0, I'm here. R can still vary, it still depends on R. Okay, and R is a positive number. So from here, if I go down, I'm measuring a positive number R because R is just the magnitude of the distance from origin and it goes up to infinity. When theta is pi, then R measured from here goes this way and parameterizes the remaining half of the z-axis. So the whole z-axis is a bad place for these coordinates. I think people are puzzled what I mean by the word bad. So the point is, if I fix theta, I expect this term to drop out from the distance function because I fixed theta, so there is no d theta. But this term also dropped out when theta is 0 and pi. That's not supposed to happen. Okay, that's the bad thing. Maybe I said it badly earlier when I said you fix theta and phi and you only have r. Well, at the origin, of course, you can only have that. But in fact, if I fix theta, even phi drops out. If I fix it only to those two values. If I fix it to some other intermediate value, then phi doesn't drop out. We also know this from the map of the Earth, where there's a latitude and there's an angle, at a fixed latitude, there's an angle which is the longitude angle, azimuthal angle, which tells me where I am. But at the north and south poles, that angle doesn't even exist. So there's not the cross section of the sphere is circles, except at north and south pole, where it's not circles anymore. So we conclude that spherical polar are bad coordinates at theta equals 0 and pi, and this is equal to the z-axis. Yes?
Why do we care one of the coordinates? So phi coordinate then becomes irrelevant.
Yeah.
Right?
Yeah. Why do we care? I'll explain in a little while why we care. In fact, we normally don't care too much, right? You have used them many times, and nobody ever wept in class because these don't describe the z-axis, because you are usually trying to describe some other part of space than the z-axis. And you didn't mind if you were describing something happening on this sphere, you didn't really care if north and south pole are behaving oddly. You can put your system somewhere else and do things in such a way that you never encounter the problem. The reason we care will become clearer just in a little while.
So we could just set a convention that we take for the z-axis phi is suppose 0.
No, that's not good enough. The point is that, so the point is this. In a space, if I set one coordinate, let's take x, y, z, the x prime, y prime, z prime, Cartesian. If I set z prime equals 0, what do I get? I get the x prime, y prime plane. So that means if I set one coordinate fixed, then the other two span a lower dimensional space. That's failing here. I fix theta, and for most values of theta, it describes a 2D space in R and phi. But for those values of theta, which are 0 and pi, it describes only a 1D space without any phi. That is the weird thing. The metric should have the property that if I fix any coordinate, I have the remaining coordinates left over to me, and I keep fixing them, then I reach a point. But here it's not happening, only at those points, and therefore the whole line. We'll see what is bad. Now, thanks to my random coordinates, we can see something even worse is possible. Look at these coordinates. So let's try to invert this to find z in terms of z prime. Z is equal to, so z square plus z minus z prime is 0. So z is equal to minus 1 plus or minus square root of 1 plus 4 z prime over 2. Right? Now, supposing z prime is less than minus 1/4. Then z becomes complex. Right? That certainly looks bad. We have not committed ourselves to any complex coordinates. All coordinates should be real. There is something called complex geometry, but it's not what we are studying. Okay, and in complex geometry, we have to admit that we are actually studying double the number of real dimensions. Like complex plane is same as 2 real coordinates. But here we are taking 3 real coordinates to describe R3, but we are finding that in the XYZ coordinates, which are defined by going from Cartesian to some new ones, in these new ones, Z prime should not go below minus 1/4. Otherwise, Z becomes complex. Also, for the same value of Z prime, I have 2 values of Z because this is a quadratic equation. Okay, so it's not a very good coordinate system. This is one of the reasons we don't use it. Okay, because it introduces artificial problems which have nothing to do with the space, just the failure of the coordinates. So the only conclusion from these examples is that coordinates can fail to describe some part of space and in fact if I gave you the length element in terms of these xyz coordinates, you would simply conclude that the space is not that of all xyz, but we have to put some restriction on xyz, and then that subspace there it works well. So it fails in some part of a space. And how would you conclude that there is that extra part of the space? You would conclude it by saying, oh, actually these coordinates can just be mapped onto these, and once you are in these coordinates, then we are free to cover the whole space. So these are better, they don't fail at all. So there is a concept, it's more advanced, and we will not get into it in this course. There's a concept of spaces being extendable, like if some region of space is not covered by coordinates like this z-axis, there's a way in which we can put back the z-axis and say, oh, now we have a better space which isn't missing some line in it. Okay, so these are all general lessons, but of course none of them has yet tackled the concept of curved space. These are all lessons about flat space. In fact, we haven't learned yet what it means to be flat space or not flat space. And we are going to do that now. Before we do that, we can do something more general. We can say, well, let me take x prime, y prime, z prime, and let me say that I'm really in favor of inventing random coordinates. What is the most general kind of random coordinate I could invent? I gave you only an example. One random and one spherical polar because it's somehow good. But I could just say that x prime is a function of all x, y, and z. And I don't specify, just an arbitrary function. Okay, I make an arbitrary change of coordinates. Now we have ds squared is equal to dx prime squared plus dy prime squared plus dz prime squared. How will it transform under this arbitrary change of coordinates? So I'll write this as using summation convention as delta ij dx prime I dx prime j. So delta ij is the matrix which sums over these two, and that's the same as that. Now I will use the chain rule. So that I lost my page. Yes. Now I will use the chain rule. So so I and j are summed over, of course. Now what is dx prime given that x prime is that? Chain rule. So it is del x prime I del x k dx k. That is this. Is that clear? I hope it's clear. And similarly dx prime is del x prime j del x L dx L. And now let me collect terms, and I can write this as delta ij. Everything is, all repeated indices are summed. That times dxj dxl. Sorry, k. I had called it k, and this is also k here. Good. So we can account, it's good to account for all indices. This whole thing has no free indices because I and j are contracted here, and k and l are contracted here and here. this is still ds squared. This is the same distance squared between the same pair of points, and this I can write for short as gkl of x, y and z dxk dxl, where gkl is simply this bracket. It's just a name for that bracket. Okay? Is that clear? So now what we say is that good. This means that while in the x prime coordinates, the distance element was created by using this second rank matrix, this 3 by 3 matrix delta ij. The distance in these other coordinates is makes use of this gkl, which is also a 3 by 3 matrix, but not a simple one like delta ij. Delta ij is just identity. There's something else. Okay. In fact, we can write out all its components painfully, or we can, for example, write them. So this generalizes everything I said before. So, for example, in r, theta, and phi, we have a matrix gkl, which is 1 here. This means there's only dr squared. Here it is r squared. It means the term is r squared d theta squared. And here there's r squared sine squared theta. Probably you have used this form. So it's a 3 by 3 matrix. And it incorporates the information needed in that coordinate system to calculate the distance. Okay? Now in these random coordinates that I invented, there were GKL was not so simple. Here it's at least diagonal but not constant. Now we see that all the properties I discussed earlier can be seen in terms of this matrix. This is in these coordinates. In the original, which I'm now calling primed, GKL is just 1, 1, 1. So here the matrix is diagonal and constant. Here it's diagonal and not constant. And in the random coordinates, it's not diagonal also and not constant, which is the most general it can be. But remember, it is symmetric. Very important for it to be symmetric. Good. Okay, so a metric in, let's say 3D, just to be, well, let's be more general, d dimensions, which could be 3 or 4 or 2, is a D cross D matrix Gij of x. When I just use x, I don't mean it depends only on the coordinate x, but on all the coordinates x1 up to xd. Such that, okay, in a given coordinate system, such that ds squared, the distance element, is Gij dxi dxj. This summarizes everything we've said up to now. Okay? And now we can derive a beautiful formula, which is that since ds squared is supposed to be invariant, it's just the actual geometrical distance on the space, doesn't depend on the choice of coordinates, this will be also equal to the metric in the other coordinate system, whatever it might be, x prime, dx prime I, dx prime j. This relates the metric in two different coordinate systems. I've already done this where one of the coordinate systems was Cartesian. Now we are not assuming that one of them is Cartesian. Both of them could be any coordinate system. Then these two things must be equal. And from the same chain rule, it immediately follows that the metric cannot be the same matrix in different coordinate systems. We already have seen that in examples. And that in fact, g prime ij of x prime is dx is G K L of x. Let me write it in this order. dxk. Maybe this is opposite of the notation I was using till now, so not to confuse you, let's do it this way. Is, I don't know which one is the one I should use. Doesn't really matter. You should be used to renaming things. It's very easy to see that if I put this into this, what will happen is these factors will combine with these to give me the dx's by chain rule, and I'll get back this invariant expression. So G has to transform. So the metric transforms as above. Under a change of coordinates. Now it often becomes difficult to remember where the prime goes and where the indices go. And here's a simple rule which will help you to remember it for all your life. First of all, this is the quantity you want to calculate. It has two indices down and it has primes. Okay. Now these two indices therefore must appear on this side again only with x prime and not with x. That's the rule. And the indices on x are always up by convention. This is just a convention, but it's a permanent convention in this field. Now here I have del x prime in downstairs, so it counts as an up index because it's counts as a down index because it's up on x prime, but it's down in this formula while k is up. These are just ways to think. Okay, therefore it matches this which is down. We have given a name for such things in our study of special relativity, and the same name applies here. This is a covariant tensor. This terminology was used by Einstein in his own papers, presumably learned from Riemann's work. So this is down, and there must be an x up because I'm differentiating one coordinate in terms of the other. I conclude from the fact that I want to calculate this, that x prime must appear here downstairs, therefore x must appear upstairs. Okay, and I repeat for the other index, and then GKL already had its indices down and they contract with this. And these are the new indices which agree with this. That's the rule. If you prefer, you can memorize it some other way, but that's just the rule of transformation. And this is called the transformation of a second rank covariant tensor. In fact, earlier we studied tensors and vectors under rotations and then generalized it to Lorentz transformations. Here we are still working only with space and not space-time. But a special case of the transformation x prime is equal to x. So x prime is I is equal to x prime I of x. A special case of this can be rotations. Just choose x prime to be linear in x and you'll get some matrix alpha ij in front of it. That's the rotation matrix. You can do that. And if you do that, you'll see how this tensor changes exactly the way that it should change under rotation to preserve the invariant length element. So the bottom line is this invariant length element should be just the same. That's why we call it invariant in all coordinate systems. Okay, and this allows us to use all coordinate systems for any particular geometry. One geometry, any number, in fact, infinitely many coordinate systems corresponding to every function x prime of x that you might dream of. Okay, but not so fast. There are restrictions. First of all, a metric needs to have a property of positivity, and that property has a positivity property. So the distance we calculate between 2 points in any space should not be negative because distance by definition is a positive quantity. So even in spherical polar, when we say that r is square root of dr is square root of dx squared plus dy squared, etc. The square root has two signs, but we pick the positive sign because r is the radial distance and a distance is a positive thing. So the metric should be positive, and that means that gij dxi dxj should be greater than or equal to 0 for any dA. Otherwise, if this isn't true, then G isn't a valid metric on space. When we come to general relativity, we'll need to relax that assumption, but in ordinary geometry, it's true. Spatial distances are positive. Space-time distances need not be positive. We already saw that. But spatial distances are positive, so this. And in fact, it's equal to 0 only if dxi is equal to 0, namely only if the 2 points I am taking distance between are the same point. Otherwise, this distance should not be 0. Okay? And there's another thing called the triangle inequality. Yes, there's a question? Okay. The triangle inequality is a little more subtle because now I have to take 2 points, 3 points, A, B, and C, and they can be finitely separated. And how do I find the distance between A and B? It's very simple. I call it DAB, and the definition is I take Gij dxi dxj, take the positive square root and integrate from A to B. So that's the distance between those points, and these need not really be straight lines, therefore I can still do this. And the triangle inequality says that if I have two of these distances, it's always greater than or equal to dAc. So the distance between a curve joining this and this cannot be greater than a curve going somewhere else and coming back. Which is suggestive of the notion that there might be a minimum distance, which in Euclidean space are the straight lines. So this is called triangle inequality, and only if this and this are true, then my 3 by 3 matrix or D by D matrix can be called a metric. So to call it to qualify to be a metric, it needs to satisfy these properties. Not any matrix can be a metric. Any questions? Yes.
Should we have more restrictions in the sense that in the change of coordinates,
Yes.
I take a set of coordinates that does not actually span the space?
Good. Thank you. Excellent question. Shouldn't we have more restrictions? Because as I've just shown, we can have coordinates which don't span the space, and we'll come to that in just a few seconds. That's a very important thing. So at the moment, take this to be a restriction for a metric in any region of a space, in some region of a space. And we'll come back to your question. Yes?
What about proper time? Can be negative.
Proper time, but we are doing spatial geometry. We are not doing space-time now. We have stepped back from Einstein and we have gone back to Riemann, who was in the previous century and did not know anything about relativity or space-time or proper time for that matter. There are analogues of everything here, but in fact these are earlier. The study of geometry of space is obviously older than the study of geometry of space-time, and it is this which Einstein together with Grossman was forced to review from 1912 to 1915. He had like 4 or 5 different papers, none of which is considered his definitive theory, general theory of relativity or theory of general relativity, until 1915, when he actually got the paper that's celebrated as his achievement. There are 4 papers before that. Yes, question.
So in metric space we have this property key d of x y has to be equal to d of y.
Good. Sorry, thank you. Symmetric also. So yeah, positive. Sorry, I forgot actually. So positivity is 1, symmetry is 2, which is actually just Gij is equal to Gji in any coordinate system, and that's enough to show what you just said, that if I have 2 separated points, widely separated, then DAB and DBA are the same thing. The same. So symmetry, and third is triangle inequality. I was a bit casual with that, but yeah, it has to be symmetric, and of course it has to be symmetric because it appears like this. This is the only place it really appears. It appears multiplying 2 line elements dxi and dxj, but these I can just exchange I and j and nothing will change because just their position will change. So therefore this I and j have to be exchangeable, which means it's symmetric. If it had any anti-symmetric part, that would drop out in this combination. So it doesn't come in. Of course, this does not stop people from asking what if there is more general metric. Papers have been written, but as far as I know, nothing particularly useful to us. Okay, now we come to the question of coordinates covering part of space. And for that, before we even do that, let's introduce a space where there are no coordinates. There is no one system of coordinates which can cover the whole space. Okay, and this space is also well known to you. Introduce a space called S2, which is R3 with R coordinate set equal to 1. 1 or any number, but 1 is just the unit sphere. It's called S2 for unit sphere, and it has the metric just this, and it's clearly inherited from the previous one by just setting R equals 1. That makes dr go to 0 because I have fixed R, and then in the other two terms the R squared term in the front of them has gone, but it's still a non-trivial metric in the sense that as a matrix, now it's 2 by 2 because we are in a two-dimensional space, the surface of a sphere, and the metric is, so now I have Gij equals this, but I have to understand that I and j take only the values theta and phi. So I and j don't run over 1, 2 and 3 or r theta and phi, they run over only theta and phi. So this is g theta theta, this is g phi phi, this is g theta phi and g theta phi. Okay. So let's introduce this space and let's try to understand it in the same way that we did before. So again, let's look for bad points. And what actually happens is that if I fix theta equal to 0 or pi, now the bad points can only be that bad z-axis which was there, but where it intersects my sphere is only the north and south pole. So the north and south pole are bad points. And let's see the technical reason. First of all, they are described by theta equals 0 and pi. Actually, 0 is the south pole and pi is the north pole. We take theta like that. And these are bad points. Same reason. If I fix theta, I expect only this term to go away, but this term also goes away when theta is 0 and pi. Okay. And now we can actually address better the question of what is a bad point. And this is part of a larger question. Okay, first let's come to it slowly. We have still a few minutes. So the north and south pole are bad points. So I have a metric on the two sphere and I can study it, but I have to keep away from the north and south pole. That's not very nice. Okay. Now, there's a theorem which is a little non-trivial, so I'm not going to try and prove it here. It's in differential geometry. There is no coordinate system on S2 that covers all of it. So unlike R3, where we could do better by just going to Cartesian coordinates and staying there, here there is nowhere to run. We have put R equals 0 and there are nothing like Cartesian coordinates on the sphere. Now this is one of the earliest discoveries in geometry because mariners who were sailing around the earth realized quickly that there's something difficult about making one map that covers all of the earth. Something apart from the fact that the earth is going to look distorted, the map can't even in a sensible way cover the whole earth. Okay, there has to be some exception, and luckily on the earth the north and south poles are pretty inaccessible places, so we are happy to do without that. We are happy with a coordinate system that doesn't cover the north and south pole. But suppose I wanted to cover the whole Earth, what would be my strategy? That's very important. What is the strategy? So can someone suggest? Zooming in doesn't help directly, because I have these coordinate systems. I have this coordinate system, theta and phi. In this coordinate system, north and south pole are not there, not valid points. So the coordinates are not valid there. Yes. Use a different coordinate system. Excellent. So first let's draw the problem. These are missing points. But of course, nothing prevents me from taking the same sphere and making a new coordinate system which is rotated with respect to this one, where the missing points are here and here. All we can see of such coordinates is that there must be two missing points, and they are diametrically opposite. But where they are is up to us. I can define a new theta and phi. How would I do it? I would start with, say, x, y, z. Okay, and there these two missing points are at z equals plus and minus 1. Okay, now I could go to a coordinate system which is spherical polar, but instead of using the formulae for x, y, z, I'll rearrange the same formulae so that z is r sine theta, sine phi, and so on. And in that case, the missing points will be at, let's say, x equals plus minus 1 or y equals plus minus 1. So they are different points on the same sphere. And here I can have one coordinate system theta phi, which works everywhere except there. And here I can have one coordinate system theta prime phi prime. I'll leave it to you as an exercise to work out exactly how you will make this, whose missing points are here and here. Okay, now what is our situation? It looks weird, but it's actually very good. If we want to study the sphere anywhere, we can use theta and phi, unless we start dangerously getting near to the North Pole. And we anticipate that, well, we want to actually go through the North Pole, which is a perfectly smooth thing to do, which our intuition tells us you can just go like that. But our coordinate system is going to freak out over there. So before that, I'll change coordinates from this to this. Okay? And now in this coordinate, nothing is going to happen when I reach the North Pole. Okay? So what is our situation? It's actually a situation of abundance. On S2, we have theta phi and theta prime phi prime available everywhere except for 4 points, except North Pole, South Pole, and let me invent a terminology which definitely doesn't exist, left pole and right pole. Okay, there are 4 points where both don't exist, but at this pair of points that exists, and at this pair of points that exists, and at all other points both exist. Now the great thing about both existing is not only do they both exist, but transforming from this to this can be done perfectly forward and backward. There's nothing missing. That is, if theta and phi covers everything here minus these 2 points and those 2 points, theta prime and phi prime equally well covers the same thing minus those 2 points and those 2 points. So these two coordinate systems can be good friends everywhere except at these 2 points where this coordinate system says, sorry, I'm out, and this coordinate system says, okay, I will take over. Or at these points where this coordinate system is out and this coordinate system can take over. So the full study of a sphere requires coordinate systems in charts. In fact, this chart is a term borrowed from sailors who use these words, such that the union of charts covers the whole, covers the space, and on the overlap regions of charts, there is an invertible map. You can go in either direction And there, in essence, this invertibility is crucial, right? Because I should be able to go back and forth between the two charts. Okay. Now, actually, it would have been enough, for example, if I found a coordinate system which covers half the sphere and a little bit more, and the other covers half, lower half and little bit more, and they just have a tiny overlap, that's also good. And you might think that if charts were expensive, then this would be very wasteful, because actually over all of the sphere except 4 points, these two are perfectly, both are there. It's wasteful, I have too many. But actually, charts don't cost anything in mathematics, and you can have as many as you like. In fact, the more the merrier in a sense. Okay, when you're actually trying to solve a problem, no, you should stick to the minimum number you need. But in principle, you can have any number of charts. So you could also define the same sphere by a metric which only exists in a small region here, and another one in a coordinate which only exists in such a region, coordinates which exist in such a region, coordinates which exist in such a region, and then I can't draw the back, but it has to, these disks have to patch up. They are disk-like, they don't even have to be disks, they can be wiggly. They shouldn't miss anything, there shouldn't be any hole, because every point of the space should be covered by at least one coordinate system. But how many you have is entirely up to you. You could have infinitely many even. And the crucial point is that it is, in practical terms, it is all the coordinate systems and all the rules for overlap, or the way they behave on overlaps, which defines the manifold. That is really the definition of what is called a Riemannian manifold. And that's what we are trying to define. And the sphere is the first example of a non-trivial Riemannian manifold, which in fact has to be defined in this way and doesn't have a simpler way to define by one coordinate system. Okay. And here invertibility on overlaps is very crucial. So this sort of answers your question. If there's a missing region that's not described by one of these coordinates, fine, just find other coordinates in that region and keep patching the manifold till everything patches. You will see that there are some consistency conditions. If you start trying experimentally to patch a sphere with little patches, your patches will go that way, that way, that way, that way around. At the back, you could run into some problems if all the patches don't have a nice formula for their overlap. For example, I can have overlap of 2 patches. I could also have a patch here. Then in this region, there's an overlap of 3 patches. So it can get very complicated, and nobody is saying you should do it. We're just saying this is how you should imagine a manifold. It's a thing which is defined by lots of coordinates with lots of overlaps, at least enough to cover it, and with good formulae, invertible formulae, even differentiable formulae. We'll do all that tomorrow, which kind of patch up everything so that actually we are talking about one object. Yes?
We patch them in a way that if one goes to, suppose that one blows up at a boundary,
Yeah.
so the other one takes care of it.
That's right. So in fact, when I draw this disk, I'm drawing it saying that I'm not going to ever use this coordinate system outside the boundary which I've drawn, and I'll make sure that where it blows up lies outside the boundary I drew it. I could draw a very small boundary also, but as long as the bad points are outside it.
So there will always be some area which you are not undertaking the
For that coordinate system.
Yeah.
But then that area will be inside another patch. So the other coordinate system will work there. And I can go from here to there by starting here, traveling till I reach an overlap, transforming my coordinates quickly while I'm in the overlap, and then continue till I reach the other point. Yes.
Why can we not use, say, here we are using 2 coordinates, why is it not possible to use, say, when I had mentioned, use a 3 coordinate system of, say, Cartesian, and then put some constraints.
Excellent question. Excellent question. So this I think takes me beyond today's time, but if you are willing to waste your lunch time, I'm happy to answer it. It's a very good question. He says we already have Cartesian coordinates and the sphere is embedded in those at r equals 1. So Cartesian coordinates will work, but with a constraint, which is xi summation over I is equal to 1. So constraint coordinates you can do. This procedure you proposed is called algebraic variety. It describes the sphere as the solution of an equation in a higher dimension. The sphere is the set of points which solve the equation xi equals 1, where xi are living in 3 dimensions, and the solution space of that equation, obviously since there is one constraint, will be 1 dimension smaller, and it will be 2-dimensional. And you can do a lot for spheres with this approach. Unfortunately, not all manifolds can be expressed as an algebraic equation in a higher dimensional space. Sometimes you may need a higher dimensional space which is not 3-dimensional but maybe 4-dimensional or more. Sometimes it really may not be possible. I don't even remember what are the precise theorems, but it is a way which you like to do when you can do it. It's very nice to do when you can do it. And actually it is one of the ways in physics we think about spheres. But we should be prepared that we can't always do that. Yes?
We were defining covering the region with charts. Did we use the fact that there is a metric defined?
Good. And the answer is no, actually. And this is something that actually most physicists don't realize. I never realized for much of my life till I started to get into this subject. You don't need a metric to discuss this issue. You just need to cover the space with a chart, with a coordinate chart. Now, you could say, well, the metric tells you where there are some bad points, but there could be other ways. You can just cover it with charts and say there are points outside this chart which I'm not going to ever try to reach in this coordinate system. So you can actually make what is called a differentiable manifold. This is the subject of tomorrow's lecture. So tomorrow, all the things I've done informally today will be written a little bit more precisely in language that won't make a mathematician break out into tears. And we'll define a differentiable manifold, and then we'll realize that, well, you can put a metric on that thing. A metric is an extra structure. So the two layers of structure are differentiable manifold just has charts. Riemannian manifold is a differentiable manifold plus a metric. And for the charts to work with a metric, you have to go between charts using the transition functions, as they are called, or coordinate changes. And under those, the metric will transform as a second rank tensor. So that's the complete story. And we just have to work out some details tomorrow and we are done. So 2 days instead of 3 years for Einstein. Yes?
Will it end up with a single metric which can describe everything? Or will
Yes, you will end up with a single metric, but it won't have a single expression in a single coordinate system. You'll have to, it's like, as I said before, if you are approaching a bad point, you quickly run away from that coordinate system to another one, and then you sail smoothly through that point, because in the other coordinate system, it's not a bad point. And you keep doing that, and you make sure that you can do that everywhere. It's highly non-trivial. But finally, you'll end up with one manifold and one metric, no matter how many charts. Yes?
Since R3 is also a vector space, what about S2 can
S2 is not a vector space.
It cannot be spanned by
Yeah.
two-dimensional basis vectors. Is that why?
Well, it can be spanned by two-dimensional basis vectors, which are the theta phi vectors, but not everywhere. Those vectors also have to do something at the bad points. That's all for tomorrow's discussion.
Is that the reason why it is not a vector space?
No, that's not the only reason. In a vector space, you should be able to add two things and get a third thing. But on a sphere, I can't add a vector here and a vector here, because the spaces in which the vectors translate are completely different. They're not even parallel planes.
Yeah.